Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to take you through a brief workflow of surface mooring analysis in the ProteusDS Oceanographic toolset. To do this, we're going to use one of the sample mooring files. This is going to be the Southern Ocean Flux Station mooring provided by Cyro. And you can see if we double click on the sample file, here we have the mooring design for this system. It's a full ocean depth mooring, so in almost 5 kilometers of water depth and almost 6 kilometers of mooring line in there. There's a lot of different connectors and a lot of different sensors on the shots of wire rope through the entire system. Some interesting frames with ADCPs on them and other instruments. So it's an example of a system that has quite a lot of complexity. In fact, probably the most complexity I've seen in any oceanographic mooring. So just to note some interesting values on top tension and anchor tension here that are good to use as reality checks as you go through the analysis process. The first step in doing the analysis, if we just verify the environment conditions, here we have a current profile that's used for the design for this system. It's fairly typical for sort of open ocean systems that aren't near any kind of ocean current, so half a meter per second at the surface and tapering off to essentially zero at full depth. And the first step is doing a static analysis and verifying the position of the mooring, which you can also do in the dynamic analysis, but the important part about doing this is using this as the starting position also for a full dynamic analysis. So when we go to static export, it'll automatically, Oceanographic Designer automatically creates the Proteus simulation toolbox mooring design for us, the numerical model of the mooring. So you can see it's in our 3D visualizer view here. We've got a very long mooring. This is just a straight diagonal line, so it's not realistic for what the profile would look like, but it's got all the elements in here for the model and all the components for floats and frames for weight and buoyancy calculations and so on. So the first step is we just hit run. And the static analysis process for this takes a bit longer than for subsurface moorings. So in this particular instance, this analysis would take perhaps 10 to 15 minutes on on a reasonably modern computer. So what we'll do is we'll just let it run and we'll check in on the process when it's finished. Okay, some time has passed and the simulation is completed. So let's take a quick peek at what the mooring deflection looks like. We'll open this up in PostPDS and load the whole thing. I'll just make this window a little bit bigger. Oops, there we go. Okay, and for such a long mooring, yeah, we'll stay in orthographic view and go to look at an east view, and we'll pick engineering. There we are. So there's the starting profile. It's just a straight line, and this is to scale because it's an orthographic projection. So the first calculation is the estimated mooring position in zero current. So there's a positively buoyant section. The wire rope will come down here, negative fiber rope, and that's roughly how it's going to sit in the water column when there's no current. And here's the profile of the mooring when we've got that particular design current that we're working with. So if you like, you can show the tension here. This is what I'd expect to see is higher tension up here where the buoy is. We've got the wire rope section here, everything goes down to basically very low tension where the fiber rope is, and then we've got a lot of glass floats to assist in recovery. So that's what the little knee is here in the higher tension region down there. So that's looking good. You could run the report tool now if you wanted to, but what I want to do is stay focused on setting up the dynamic load. So this is why it's really important to do a static analysis first to get a realistic profile to start the dynamic analysis from, and then you get more realistic dynamic load results and motions from the mooring than if you just run it with a straight line and start it off. It did take a really long time for it to relax to this shape. And then the simulations take a long time to run, and you aren't certain if you've got the maximum loads or not that way. So what we do here is, let's just close a few of these other windows here. We will need to click on the export button, export final state. And it's going to take the final state from the simulation, so we'll call this dynamic. And I'm just, for convenience, going to save it down in this folder here, separate from the static analysis. So we got another folder there. Okay, so I'm going to close the old project. Now we have a brand new project, and we need to do a little bit of work to get this ready for dynamic analysis. So now it may look like a diagonal line from a certain perspective, but actually in the pre-visualizer you can see it's got that curve to it, and there's the little knee with the acoustic release. So we're going to start our dynamic analysis with waves in this with the starting condition. One of the things you need to do is we need to convert this d-object from the static model to the dynamic model, so quasi-static cable to cable, and we'll save that. So the cable model is our fully dynamic finite element model, and you also need to change the simulation parameters and pick a suitable length for your simulation. Probably something longer than 200 seconds would be good for a full ocean depth mooring, maybe something like 750 seconds. It just depends, and you need to run more than one realization, but that's another topic for another day. But this will be reasonably representative for getting the dynamic loads. And we need to turn on waves as well. So under the environment tab here, we have wave type. I'm going to pick, we'll just pick an irregular sea state like John Swap, and we'll resolve follower properties. Here, I'll pick something quite severe, 9 meter significant wave height, 13 second peak period. That's reasonably representative of the most severe steep conditions in the Southern Ocean, where this mooring is too. And we'll save it, and I think we're good to go, so we'll run it. Now you get a little bit more visual feedback on what's happening in the simulation with the progress bar. As it's running, you'll see this blue bar starts to fill up. So we'll let this run for a while, and then we'll check on the results. Okay, so some time has passed, and now what we want to do, let's take a quick visual check on this mooring. We'll open PostPDS again. You may not want to load the whole time series, so you can pick some options here to just load a certain amount of time, and it reduces the amount of time it takes to load the file. Here we go. And we'll just make this window a little bit bigger. We'll go to engineering view. And now, very generally, you can see because full ocean depth, the wave height's not necessarily that big relative to the water depth, so it's not like you can see necessarily a lot of effect on the mooring. But if we look at the tensions, you can see there's quite a lot more dynamic variation happening as the system is subjected to these wave loads. And this is only 50 seconds of the total time series that we looked at. So we can also take a closer look in perspective view. Double click on the buoy, double click on the cable, and it'll take us to the end where the top buoy is, and we can play this back just to get an idea of what's happening and see how the buoy's tracking the waves well, and see what's happening. You can do some plotting too if you like. So we're plotting tension, element 1, and you can see there's actually we captured a shock load here, so that's interesting. If we go back to 178 seconds, I think we just passed it actually. You can also get this information from the report tool, and then it's kind of interesting to go back and look at it. So it says there's a shock load around here. Let's just see what happens. So big wave is going by. That's typically what happens. Yeah, the mooring is getting unloaded, so the tension's getting very low, and then it gets slammed when the whole system accelerates back up this kind of steep wave. So that's just typical kind of dynamic loading in this kind of the scenario when there's lots of accelerations and pretty steep waves. Okay, so that's nice to see, but it's nice to have a report that summarizes this and post-processes this. That's when the Oceanographic Report tool comes in handy. And this will give us the results. And there's so many components in here, it's nice to be able to filter down to a few key ones in the summary page. So we'll pick the buoy and then a couple of frames which have ADCPs and other current meters in them. And what I like to do is you should really skip the first 10 seconds where we have ramp up of wave conditions and any artificial transient effects from the conversion from static to dynamic model. So we'll it just ignores the first 10 seconds of the simulation and then calculates the statistics and checks for maximums everywhere else. So we'll click generate. And then we'll open the Excel file that's been generated from here. And you'll see that there aren't any lines below the minimum safety factor. And it's checking for components that are below safety margin for those that have a working load limit as well. You get a summary of, so we picked a few of the frames here, and you can see the maximum tensions for those in tons. And if you want to change the units, you can change the units back up here for parts and attachments. So we change that to kilonewtons. You can see now we see max tension here for those components in kilonewtons. And then we have the maximum horizontal excursion for the surface buoy, 3,500 meters. So that's maximum with dynamics. So the mean position is kind of also indicative of the watch circle, depending on how you want to look at it. And there's also the watch circle directly reported out of here as well, which is going to be based on the mean value. Vertical excursion, again, there's going to be just from the motion from waves, you're seeing some variation from that. And yeah, if you want to look at anything more specifically, you can click on line and see all the line components and the resulting safety factors. So we're seeing lots of safety factors in 5, 7, and things like that, and so on. So just wanted to show an example of a workflow of the process for a surface mooring, particularly for a long and complicated one, when it's important to start with a static analysis and transition that to dynamic analysis. Thanks for watching.